Good afternoon. Welcome to our lecture on applications of data science and software engineering. As you know, this lecture is going to be recorded, so you probably will see the red button on your screen. So today we are going to discuss selecting people, companies, projects, or artifacts for our study. But before we go into those details, I would like to ask you about the first quiz. How did this one go? Please feel free to type in the chat. Did you have enough time? Did you find the questions easy or difficult? So I see several people are typing. Okay, so what do we see? Yari says I had enough time. Some were more difficult than others. We will be able to see the correct answer. So the answer is yes, you will be able to see the correct answers. Medium level difficulty, the time okay, all good for me. It was a bit tricky, but the time limit was fine. Q3 and Q4 were more difficult to analyze. Okay. Let's wait for a couple of more seconds. I had enough time with this lecture. The questions were easy to understand. Some articles were tricky. Well, this is indeed part of the story. So first of all, I'm very glad to hear that you had sufficient amount of time, because this was one of my major concerns here. The fact that some of the papers are more difficult to understand, it is part of life. Not every single paper makes methodological decisions as explicit as apparent as they strictly speaking should be. But this is also something which will help you to read those papers. So during the course, in the upcoming quizzes, you will be expected to read additional papers and to analyze them, for instance, to see what kind of sampling strategies have been used, or what kind of okay, so we are going to publish the answers on Canvas. We are also going to check the most frequently mentioned erroneous answers and try to explain why do we think that those answers were erroneous. And feel free to reach out to Nathan and me on Slack if you have further questions. The best way to reach out to us on Slack is to create an individual channel for 3 people. So you, Nathan, and myself, such that either Nathan or me can answer your questions. I could interpret the approach in multiple ways, or rather a mixture of multiple types. So Nicoletta, it's a very valid point. Some studies might involve multiple research strategies, even though we have tried to select those which are relatively clear-cut in this respect. So thank you for your feedback. Let us move to the topic of today's lecture. So today we are going to start the discussion of data collection techniques. So as you remember from the first lecture, we have always been making this separation between data collection and data analysis. So the data collection part will consist of 5 lectures. Today we are going to talk about today is the first one. So we are going to talk today about sampling. Right? You might remember that in almost all studies we have discussed during the first lecture, there was an attempt to somehow reduce the number of points, people, projects, sources to a more manageable number. And this is a process we know as sampling. So formally, sampling is the process of selecting a smaller group of items to study from a larger group of items. And the smaller group of items is known as a sample, and the larger group of items of interest is known as the population. So one might wonder what research strategies require sampling, and in fact, all of them. If you are conducting a field study or a field experiment, of course, you need to decide which field or which fields to consider. So what company, what project, and so on and so forth. If you are in the laboratory experiment, you might remember that you somehow need to decide which participants to select. You might have special constraints which determine what kind of participants are allowed to participate in the study and what kind of participants are not. If you are conducting a judgment study, you might recall that we need to look for experts. So, of course, separating those experts from a broader population is already sampling, and so on and so forth. In fact, even for a formal theory, we need to select the literature to derive the theory from, which can be seen as a form of sampling. So when we are talking about sampling, usually we make distinction between three notions: population, sampling frame, and sample. So as you remember, sampling is a process of selecting a smaller group of items to study from a larger group of interest. So this larger group of interest is a population. This group of interest is usually represented by some kind of imperfect list. And this population list is known as a sampling frame. So on the slide, we have a crowd of people, have a list of names in some kind of book, which can be seen as a representation of those people. And then, of course, we have a sample, which are essentially people we have somehow selected based on this sampling frame. So this is at least how sampling is supposed to be done. So software engineering is difficult in this respect. So let's say we want to study open source project. So we already break at the level of the sampling frame because there is no sampling frame. We don't really have an absolute list of all open source projects in the world. And there is no way we are going to be able to. Okay, so. Just a sec. Just a sec, I'm still sorry. I'm sorry. Okay, if you are going to study Git, I apologize. If you are going to study Git and GitHub, this sampling procedure is not necessarily easy because, of course, if you want to study contributors to GitHub, they might have multiple aliases. If you have a project that is stored on multiple repositories, we need to be able to know which repositories correspond to the project. And sometimes one repository contains multiple projects. So even in presence of the sampling frame, which is the case for GitHub, identifying the sample is not easy. So this was a brief introduction to sampling, and the remaining part of the lecture will be dedicated to discussing different sampling strategies. Because, of course, depending on what kind of sample you look for and what kind of situations you are, you might employ some of those and not others. So let me give you a brief overview of the sampling strategies. On the blue background, on the left, we have non-probabilistic strategies. We are going to start with them. In the middle, on the green background, we see probabilistic strategies. As the name suggests, all those sampling strategies involve some form of randomization. On the right, with a pink background, we have multi-stage sampling strategies, which typically combine probabilistic and non-probabilistic elements. Finally, at the end, we'll have this panel sampling, which is pretty much independent from probabilistic or not probabilistic, or maybe combined, and it's essentially about how to run sampling rounds. So we start with the simplest sampling, which is the convenience sampling. So in general, in the convenience sampling, items are selected based on their availability or expedience. And when we select for people or artifacts to study, for instance, them because they're nearby, because they're available, or because otherwise they are easy to study, we in fact adopt convenience sampling. Something like interviewing 5 people because those people happen to be my own graduates is a convenience sampling. So convenience sampling is quite common in software engineering research. Here are a couple of examples. So in this study of biometrical measurement of emotions, which has been conducted by colleagues at the University of Bari in Italy, they have recruited 27 students, 23 men, 4 women, from the Department of Computer Science of their university. 21 were undergraduates, 5 were graduates, and 1 postgraduate. So essentially, the reason why those students have been recruited is because they have been available. So it was easy for researchers to ask those students to participate in the experiment. But it's not necessarily about people. Selection of projects might also be performed through convenience sampling. For example, in the study of Hunsen, the authors wrote that for industrial systems, they had less choice and had to rely on convenience sampling, which biased the selection of industrial systems towards embedded systems domain. So ultimately what this means, we have been able to analyze what we were able to get. Getting any other kind of project was difficult, and this is essentially convenience sampling. Of course, convenience sampling has lots and lots of advantages. First of all, it is fast and it is cheap. It is fast in a sense that we can relatively easily identify students who might be ready to participate in this biometric study. We can easily pick up 5 favorite projects, or we can talk to a company that might give us 1 project they might be interested in sharing. So it is fast and it is cheap. Moreover, there is no need for sampling frame. So recall that sampling frame is a representation, more or less perfect, often less and more, a representation of the entire population. We will never be able to obtain a population of all software developers in the world, or even in the Netherlands. We will never be able to obtain a list of all open source projects. So convenience sampling alleviates this problem because for convenience sampling, there is no need for a sampling frame. However, convenience sampling, of course, has its limitations. There is no statistical generalizability. And if you are talking about people, it is very easy to obtain biased results. For instance, if you are going to interview people who have studied, only people who have studied in Eindhoven, they might share some kind of attitude towards certain software development aspects, which can be traced back to courses they all have followed. And another example is, of course, what you have seen with the previous paper, when the authors have indicated that their sample of industrial projects was biased towards embedded systems domain, simply because those were the projects that were available. So ultimately, convenience sampling is very, very popular, especially in laboratory experiments, but also quite controversial. So it makes sense that convenience sampling would be your weapon of choice for exploratory studies. If you just want to understand in general lines how the things work, what kind of phenomena are we studying? Alternatively, convenience sampling can be fine if we are trying to study universal phenomena. If essentially what we are trying to study is related to us being human beings rather than developers using specific technology in a specific organizational context. For example, cognitive biases, which are related to how human beings make decisions, are related to decision making in general, as opposed to specific technological problems, even though those decisions can be taken in a given technological context. So this means that if our goal is to study cognitive biases, then we still might use convenience sampling, even though this might not be appropriate for other kinds of studies. Let us continue with the discussion of purposive sampling. So purposive sampling is a sampling where items are selected based on specific characteristics other than availability that makes them relevant to the study's objective. So we start with an objective, and based on this objective, we derive several characteristics which can be used to select the items on the study. For example, in this, so on the slide, you see a page from the dictionary, and if you are interested in studying nouns, then we can select the words which have been encircled in red. In general, of course, selection can be more intricate. It can involve some logic or strategy, but this logic should not be random. The goal, of course, of this non-probability sampling is to find accessible and information-rich cases. And this case can be indeed a person, this can be an organization, this can be a context, whatever we might be interested in studying, as long as we can study it. So let us look at the ways purposive sampling can be conducted. So the first study is our own work from 2015. So, and then we have chosen to study GitHub projects because GitHub was the largest ecosystem of its kind. It has a wealth of trace data available and is known to promote technology. We've been studying change, right? So in this case, it is a purposive sampling because we have clear criteria which explain why we want to study this particular element, this particular platform. Sometimes the goal can be to select projects that are as diverse as possible. So essentially, the criteria we are looking for are not applicable to an individual project, but to the collection as a whole. This is also known as heterogeneity sampling. Even more, we might consider extracting the sample from a large repository by using a specific query, search query. So for instance, here, I was just looking for papers about code reviews, starting from 2006, published after 2016. So this means that in this way, we can sample, in this case, scientific papers, by using a specific query provided by Google Scholar. So this is a query-based sampling. It is quite common when conducting literature reviews, but not only literature reviews. And finally, you might remember that in the study of risks related to offshoring, participants have been recruited because they had a certain expertise. on a specific topic. This is what is known as expert sampling. So all those methods, for instance, studying project hosted on GitHub because it's popular, because it has full support, heterogeneity sampling, query-based sampling, and expert-based sampling are known as forms of purposive sampling. In general, we can say that the advantages of purposive sampling are related to the fact that the researcher can exercise their expert judgment. So essentially, the researcher knows what kind of items they want to study. Is this a large project, or is it a person with a specific expertise in a specific domain? Or maybe it's a collection of people or projects exhibiting different features. Second, the researcher can ensure representativeness of the sample with respect to a specific domain, with respect to a specific dimension. So for instance, if I'm interested in collecting projects from different programming languages, one way to achieve this would be to select one Java project, one C project, one Python project, and so on. And again, for purposes of sampling, we don't really need the sampling frame. We just say we select this project or this person or this group of projects or this group of people because, and then we explain why we have selected those. Of course, the limitations of the purpose of sampling are also quite apparent. So in the same way as with convenience sampling, there is no statistical generalizability. So conclusions can derive based on purposive sampling cannot be generalized in terms of statistics. It also means that the sampling is intrinsically subjective and opportunistic. Very often, things like expertise are hard to capture in an objective way. And while the advantage of this purposive sampling is that the researcher can put themselves as an expert to claim what is going on, at the same time, the researcher cannot be completely objective in this sense. So again, it is something which is, so purposive sampling is a method which is beneficial for exploratory studies and for studies of universal phenomena. So let's ask a question. So I have put a snippet from a scientific paper on the slide. And the question to you is whether this is a convenient sampling or purposive sampling. I'm going to start a poll. Okay, so let us see what are the results. So roughly 2/3 of you see this is a purposive sampling, and roughly 1/3 thinks that it's a convenient sampling. Would maybe one of you can try to explain why do they think that this is a purposive sampling or a convenient sampling? So this type. Okay, so Olaf says that it's a purposive sampling as we want to research commits, hence we select project with the most commits. Anyone in favor of convenience sampling? Top 50 seems to be picked arbitrarily. Yes, so I believe that this is a purposive sampling. So the purpose of this study was to select projects with a high number of commits. We can argue whether the selection criterion was reasonable or not. So one could have said, we don't, 50, it's not enough. Maybe we should have been doing a different sampling. But as a sampling as its own, it had a goal. In the meantime, I have also noticed a question in the chat whether the results that are biased, whether something which produces biased results can still produce reliable outcome. Yes, it depends on the interpretation of the word biased, and also depends on what kind of reliability are you looking for. For instance, creating in a judgment study, you would like to talk to the experts. So experts are nowhere representative for the population in general. So in a way, selection which favors experts will be biased. But you're not looking for generalization over the population, you are looking for generalization over the ideas. So the outcome in terms of diversity of ideas, of diversity of opinions, might be what you're after. Okay. Let us continue. So the next sampling method we are going to look at is a snowball sampling. So snowball sampling, in the snowball sampling, items are selected based on their relations to previously selected items. So and the idea is very simple in the sense that you start with a small group and of items, whatever they might be, and then you are checking related items, and then you are slowly growing your snowball, and then you are growing it a little bit more, and a little bit more, and a little bit more. Essentially, this typically means that during the interview, you ask your interviewee whether you can nominate other people that the interviewer might like to interview. But of course, it's not necessarily the case that we are studying human beings. Maybe we would like to study libraries, or maybe we would like to study scientific papers. In this case, the notion of referral is, of course, different. For instance, we can say that one project is referring to another one if it depends on it in terms of import statements. Snowball sampling is quite common in literature studies, and is usually used to supplement query-based sampling. So you might have seen in one of the previous slides the example where we've been thinking about papers about code reviews, which have been published in 2016 or later on. So let us say we have performed the first step, we performed our query-based sampling, and we have identified a series of papers on the left-hand side. Those 4 papers, like Modern Code Review, a case study at Google. So we would like to augment this collection of papers because maybe we do not trust that our keyword-based search has correctly identified all papers which are relevant. So typically what happens then, we perform backward snowballing and forward snowballing. So backward snowballing would mean checking the papers cited by the paper we are focusing on and selecting among the papers cited those which might be relevant for the topic of our work. So for instance, in this case, this would mean going through the list of papers going through the list of papers which have been referenced by the paper by Caitlin Sadowski and her co-authors, and checking one by one, is the paper relevant or is the paper not relevant for code reviews. So for instance, we know that reference 2 is about software inspections, which is not exactly code reviews, but reference 4 and reference 8, they are about code reviews. So we would include references 4 and 8 in our ever-growing snowball. A complementary method would be forward snowballing. Tools such as Google Scholar allow us not only to check which papers have been cited in a given paper, but also which papers cite the given paper. So on the upper part of the slide, you see a series of papers which cited the paper about modern code review. So again, we would be going through the list of papers which are citing the paper in focus, and then we are going to decide, is this paper relevant or not? If it has been relevant, then we add it to our ever-growing snowball, and ultimately we repeat the entire process much in the same way as we have done before. Of course, the question is, where do we stop? And the answer here is that as long as there are no papers which satisfy our relevance criteria. As soon as we see that all papers have been found, we can stop. Again, as you can imagine, this process can be often very labor intensive, but this is one of the common techniques of conducting literature studies. So let us summarize what we know about the snowball sampling. First of all, it allows us to go beyond the sampling frame. So by exploring the references, we no longer need to assume that we have this kind of perfect sampling frame which will tell us what elements are part of our population and what elements are not part of the population. This also means that we can reach hidden populations where we can be sure that there are no lists of no sampling frames are available, or in case of people might be reluctant to disclose that they are part of this group. In a way, this kind of snowball samplings or improved version of it, which we are going to see in a moment, the so-called respondent-driven sampling, are popular when studying, for instance, people having specific kinds of diseases, drug users, and so on. So let us look at the problems which might be caused by snowball sampling. So if this is how our population looks like, then we can be pretty sure that the item D1 is highly likely to be selected, because snowball sampling will essentially try to traverse those referral links, and independently from where you are in this graph, after maximum 3 steps, you can reach D1. So the snowball sampling has a bias towards better connected items. Moreover, if you start with B3, it is very likely that that you are going to explore the B space first before going to the A space and the C space. This means that the features of the project in this B space or opinions of people in this B space will dominate their general perception of the phenomenon we might have been forming. This is why a better way to perform this kind of referral chain sampling is the respondent-driven sampling. First of all, to avoid the problem of selecting D1 multiple times, we need to agree that every person or every project or every item can only be selected once. Second, to solve the problem with this strange selection of B3, which has an implication for how we look at the world in general, we need to start with a diverse set of seeds that do not know each other or that do not refer to each other, are well connected, and if we are talking about people, can actually influence people. Influencing people would essentially allow us to explore this graph. And another point we need to keep in mind is that if B3 recommends us B2, B1, B5, B4, and so on, we are still stuck in this B space. This means also that we need to limit the number of recruitments, so the number of referrals every person can provide or every project can provide. And this way we will increase the number of iterations or the number of waves so that will go through this entire graph. So how would this respondent-driven sampling work? We will start with a set of diverse initial participants. As I said, those participants should be representing different subpopulations, do not necessarily know each other, can influence peers, and so on and so on. So for instance, if I would like to study how software engineering students perceive group projects in Dutch software engineering education, I will start by selecting one student from Delft, one student from Eindhoven, and one student from Twente. This could be one possible way of identifying seeds. Then I will ask my students to recruit their peers rather than identifying them, because this will essentially reduce the selection bias by the researcher, and also because those participants can influence their peers and encourage them or convince them to talk to the researchers much more than whatever a researcher will be able to achieve. As I said, we need to limit recruitment such that each participant can only recruit a small number of peers, typically 3 or 2. This will essentially prevent highly connected people, such as D1, from biasing the sample. We need to require many iterations or many recruitment waves. Typical guideline here would be 20 recruitment waves, but of course it takes a lot of time. So you need to be balanced, and you need to balance the feasibility expectations and the quality expectations. In any case, longer recruitment waves will result in longer referral chains, which would decrease the risk of oversampling from a highly connected subset of the population. And indeed, we need to continue this process until the sample has reached an equilibrium. So essentially, at some point, the distribution of variables of interest is stable. At some point, the opinions we have been hearing have converged. So this is where we can say that the equilibrium has been reached. So similarly to the snowball sampling, respondent-based sampling allows us to reach out to hidden populations. It has advantages of not being limited to the sampling frame, and it has also been designed to address the shortcomings of snowball sampling we have been talking about. At the same time, snowball sampling and respondent-driven sampling violate the basic premise of statistical analysis, namely that a sample which we are going to analyze is a random sample, because this is not a random sample. Is it probably as not random as it possibly be? this also means that classical statistical analysis techniques are not applicable. So if you want to do statistics on the data which has been obtained by means of respondent-driven sampling, then more advanced statistics should be used. Okay, and then again, it's a question for you. So we have 4 options, A, B, C, and D. And the question to you is, what kind of sampling strategy has been used by the authors? Oh, yeah. Okay, yeah, I need to be careful when asking questions with in terms of order of, yeah. Okay, so let us stop here. I see that 9 participants believe that this is purposive sampling, 4 believe that it is a respondent-driven sampling, and 2 believe that it is a convenient sampling. So this is a purposive sampling. There is no discussion whatsoever of referrals of any kind. So this is why it is not a snowball sampling and it is not a respondent-driven sampling. Why is it a convenient sampling or a purposive sampling? The word because it is one of the applications with the largest number of BMs, and also because it is well documented. So those things indicate that there is a purpose. There is a reason why those and developers have been set because this J groups application has been selected, and those reasons go beyond availability. Okay, next question. And this time again for answer options: A, convenience sampling; B, purposive sampling; C, snowball sampling; and D, respondent driven. Okay, so what do we see here? We see one person believing that it's a convenient sampling, one person believing that it's a purposive sampling, and then the remaining group is more or less equally split between snowball sampling and respondent-driven sampling. So I would say that in this case, you have a 2-stage sampling process. The first step was identification of those presenters at the data-driven engineering meetups. And those presenters have been identified because they have been responsible internally for sharing best practices. So essentially, this means there was a purpose why those people have been selected. Next, the authors have selected additional data scientists by word of mouth. So the word of mouth is essentially an indication that there is some kind of referral process. So it is not surprising that most of you believe that this is a snowball sampling or a respondent-driven sampling. However, here, there is no indication that special care has been taken to go for respondent-driven sampling. There are no references to things like reducing the number of introducees, increasing the number of recruitment waves, or anything along those lines. So I would say that in this case, we have as the first step of the sampling procedure, we have a purposive sampling B, and as a second step of the sampling procedure, it's a snowball sampling C. So the next group of the next group of strategies is probabilistic sampling, and we are going to discuss them after the break. So let us resume the recording and let us continue our discussion. So the probabilistic sampling is a technique which is based on the idea that we can randomly select items from a list. So in this case, it means that first of all, we need to have such a list. So we need to have a sampling frame. Without a sampling frame, probabilistic sample is not really possible. And second is that we actually have a random selection. And the random selection is really random, meaning there is a random number generator involved. Standing on a street corner and interviewing random pedestrians is not random in statistical sense, because of course you are going to miss people who are not pedestrians. Think about car drivers, think about cyclists, think about people who are using public transport. Even if you can somehow interview all kinds of people in terms of what means of transport they are using, your selection will still be influenced by time of the day, time of the week, period, weather, and 1,000 of other factors which you cannot control. So moving to software engineering, recruiting participants using an email or advertising on social networks, it's not random. For example, if I'm advertising things on Facebook, then I'm not going to reach out to software developers in countries which ban Facebook. If I'm going to sample people from LinkedIn, I'm going to miss people who are from countries who ban LinkedIn. I'm also going to miss people who self-select not to be present on this kind of platforms. We cannot expect every single software developer to be necessarily involved in social media, even though many of them are. Assigning participants to an experimental condition as opposed to a control condition is not random. For instance, because you might be favoring people who are better organized and arrive on time, as opposed to people who arrive later. And those differences in personalities or might be influencing whatever you want to observe. So essentially, without a random number generator, it's not real random sampling. So the first type of random sampling is just a whole frame. So essentially, we take the entire frame as a sample. This is, of course, kind of debatable whether an entire frame sampling can be seen as a probabilistic sampling, but it is still an important point to reflect on, in particular for small sampling frames. So An example for a whole frame sampling would be contacting all employees of a specific software development company, or analyzing all questions on Stack Overflow, or analyzing all commits over the entire GitHub, or all commits over a specific GitHub repository. So, of course, the whole frame sampling has a huge advantage in a sense that it is as complete as possible, right? I mean, if we can reliably analyze the entire sampling frame, and if the sampling frame is reliable, meaning it reasonably well represents our population, then why shouldn't we be doing it? But of course, this kind of analysis is not feasible for large populations, either not feasible at all, or not feasible within the reasonable constraints of time and effort. I mean, next, on Thursday, we are going to talk about interviews. Yes, you can interview 20, 30 people, but you cannot interview 2,000, 3,000 people unless you have an entire army of the interviewers. Moreover, such a whole frame sampling is not feasible for poor sampling frames. And poor sampling frame means essentially incomplete frames. So we do not know what is missing from our frame, but we kind of suspect that this is the things which are missing, or inadequate. So we know what is missing, but it is clear that the sampling frame is very different from the population. So an example of an inadequate sampling frame would be, for instance, public GitHub repositories, as opposed to all GitHub repositories. So if our goal is to derive some kind of conclusions about all GitHub repositories, we cannot use public GitHub repositories to derive those conclusions, because this sampling frame is not adequate. So if our sampling frame inadequate or incomplete, then we should not be using whole frame analysis. Okay, a more popular technique is a simple random sampling. So items are selected entirely by chance, such that each item has equal chance of inclusion. So let's say we are studying a morale in a software development company, and our first attempt was to try and run a survey for all the employees. Let's also say that the survey did not provide results we've been hoping for, and we would like to go deeper. But of course, to go deeper, we need to conduct interviews, and conducting interviews is not plausible if our company has something like 10,000 developers. So essentially what we are going to do, we are going to try to allocate every single developer a number, and we are going to, between 1 and 10,000, and we are going to use a random number generated to select 20 developers and essentially interview those developers. It's a simple random sampling because the researcher is not doing anything else than simply choosing n random elements from the population. An example of such a study which has conducted, which applies this kind of sampling strategy, is by Gordon Fraser, Andrea Arcuri, who have randomly selected 100 Java projects from SourceForge, a well-established open source repository. So this looks more or less reasonable, but of course the question is 100 enough? Luckily, we are not the only people in the world who are doing random sampling, and our friends from statistics have designed all kinds of methods and tools to help us. So this is an example of a tool. I'm not going to discuss with you today what kind of mathematics is behind the tool. I will discuss it later on. But what's important for you to understand is this kind of tools allow one to determine the sampling size based on 3 parameters. One of those parameters you already know, and this is the population. So 10,000 developers in a company, or whatever, roughly 50,000 projects, for instance, on SourceForge, or so many millions projects on GitHub. Two other variables are confidence level and confidence interval. So confidence interval, it's essentially a margin of error. So what your sample, so if you have sampled the relevant number of people, and if your sample is indeed random, then you can be confident that the true percentage of people who, for instance, say yes to your question is not more than one confidence interval away of the reporting based on the sample. So essentially, if your study shows that there are 25% of the respondents who are saying yes, and your your confidence interval is 5%, which is very common, then you can be sure that it's 25% minus 5 plus 5, so it's between 20 and 30%. The other variable is the confidence level. So essentially, you can see it as a degree of confidence that you might have that the true percentage is indeed not more than one confidence interval away from the percentage which has been reported based on the sample. So after this very brief primer on sample size, let us see what happens in our study. So I have chosen the traditionally used confidence interval of 5%. I have used a relatively low confidence level of 95%. I filled in the number of projects on SourceForge in 2014 because this is when the paper has been published. And the number of projects that the authors should have included in their sample was 381. So already at this level, we see that random sample would have required a more significant effort than what the authors were able to spend. So, unfortunately, the conclusions of the study are not statistically generalizable. So ultimately, if we are talking about simple random sampling, we, of course, have the major advantage of statistical generalizability, under the assumption that this random sampling has been done right, and not as it was the case in the paper I've been citing. As already mentioned, it is not feasible for poor sampling frames. The argument is the very, very same argument as for the whole frame. If the sampling frame is not adequate, then no sampling based on this inadequate sampling frame can help to remediate this. The idea here is, of course, that this random sample is somehow seen as a representative, quote unquote. Representativeness here is a very difficult matter. In a way, representativeness is a degree to which the properties of a sample resemble those of a target population. And obviously, a sample can be representative with respect to one dimension and not with respect to another dimension. There are tools which allow one to select, for instance, software engineering project samples based on a large data collection, such as the distribution of variables such as size or programming language for the sample will be representative with respect to the large data collection. We should, of course, be aware that representativeness with respect to easily observable properties, such as lines of code, do not necessarily imply representativeness with respect to much more difficult to observe properties, such as, for instance, complexity of discussion of those lines of code during code reviews. And of course, again, probabilistic sampling does not really guarantee representativeness. If it's a simple random sampling, there is absolutely no guarantee that you are going to select both small and mid-size and large projects. Merely because of the choice of the randomness, because of the randomness factor, you might end up with having only small projects or only large projects. So in a way, a non-probabilistic sample can be more representative with respect to the property of interest. Statisticians actually rerun this kind of studies for many samples, but this, of course, is often unfeasible because multiple samples will require repeated analysis. So a slightly different variant on the random sampling theme is a systematic random sampling. So in this case, the sampling goes in two phases. So first of all, we randomly select a number, and then we select every certain number in the series. So essentially, if you have chosen, for instance, the first number, and the first number is 100, then we essentially we select the entire second column in those letter boxes. So we typically select something like every nth item in a series. This is quite common when we are analyzing time series. For instance, when we want to say we're going to look at every 20th commit to a repository. As you can imagine, this will become a systematic random sampling only if the first commit has been chosen at random. If we start with the very first commit in the repository and then select every 20th commit, we will of course might have some kind of bias there. In a way, every item still has an equal probability of inclusion, but this probability is completely determined by the first random step. When can this kind of behavior be problematic? If the consistent interval, like for instance, every 8 mailboxes in the picture, tends to coincide with some kind of rhythm of the project. So for instance, just a very simple example, let's say you are studying weather. If you are always measuring the average temperature in July, then you might have a very different picture than if you are always measuring the weather in January. So how does it play in software engineering? As I already said, it is typically being applied when we are studying time series. So Carl Chapman and Katie Stolley have said that they did not want to scrap all commits in every project, but rather they grabbed every project every 20 commits. So indeed, advantages, disadvantages. Major advantage is that every item still has the same probability to be included, but there can be risks related to the sampling interval coinciding with the project rhythm, such as the release cycle. Good. Let us give the stage to you. So here we have yet another quote from a study, this time by Mario Linares Vasquez and his co-authors. And Mario and his co-authors were studying exception hierarchy of Android APIs. And the question to you, what kind of sampling strategy did they use? So it's interesting that all answers have received at least support. So one person believes that it's snowball sampling, 2 people believe that it's a systematic random sampling, the majority believes that this is a simple random sampling, and finally the last group believes that this is none of the above. So I'm not sure that I understand why is it snowball sampling. There is no discussion of references. This is also not a systematic random sampling because there is no indication that those 360 commits have been selected according to whatever repeated pattern that they might have in mind. I would argue that it's a simpler random sampling, simply because there is no information whatsoever about how those 360 items have been selected for manual analysis. So I understand people who say none of the above, but in a way, you kind of would trust the authors to perform simple random sampling. But this is, as you see, this is the difficult part, right? So scientific papers are not necessarily including all the information you might need to understand what was essentially going on. Partially, it is related to the limitations of the space. So every paper has a certain maximum number of pages it can occupy. And at the same time, it can also be related to authors simply missing details in the description. Okay, let's continue. So our next group of strategies, sampling strategies, are multi-stage sampling, and multi-stage sampling is a special case where two or more sampling strategies are intentionally combined in the same way as two different trains are combined on the slide. So the first picture here, the first slide here is related to the stratified quarter sampling. So the sampling frame is divided into subframes with proportional representation. So let me make it a little bit more tangible. So let's say we want to continue our study of developers' morales survey. And let's say that there are differences, we observe differences between developers who identify as white and those who do not identify as white. Moreover, in our organization, 90% of the developers are white. So, of course, if we would perform some kind of random sampling, we might end up sampling only the majority group, which is not a good idea if you want to understand differences between the groups. So, in this case, a researcher would better divide the developers in two strata, two subpopulations, in this case, white developers and not white developers, and select 10 developers from each stratum, such that they can be interviewed, for instance. If developers within the stratum are selected randomly, then this is a stratified random sampling. If developers are selected purposively within stratum, then it's a quarter sampling. So essentially, it's a multi-stage sampling strategy because we first of all need to select those strata, and then we need to select people within those strata. So what do we have here? We have nice sandwiches and some nice desserts represented on multiple plates. So each plate here is a stratum. We first of all decide to organize our food in those plates, and then we are going to sample elements from each plate. This would work as long as our strata are homogeneous, but very different from each other. So if you look carefully at the image, you will see that at each plate, at each level, the food is essentially the same, but they are different from each other. So if this is what we are interested in, then stratified random sampling or quarter sampling is the way to go. Let us move from sandwiches to software engineering. Here's an example of a paper. So the authors have recruited 42 participants. Out of those 42 participants, 12 identified as women and 30 identified as men. So gender is, in this case, determining the strata. women, men, and non-binary people. And of those participants, there was a sampling. So 10 participants have been sampled among women, and 10 participants have been sampled among men. And there were no non-binary participants in the first list, so there were no non-binary participants in the sample. So this is a quota sampling because the participants have been selected purposely. And this is also the case because and this is also the case because and also the case that representatives from the majority group are less likely to be selected, right? So men are less likely to be selected than women. Another example is the stratified random sampling. This is a study by Venera Arnaudova and her co-authors on identifier renaming. So first of all, they have grouped renaming based on what kind of entity has been renamed, type or method. Those are our strata kind of entities. And then they randomly select the sample from each group based on those kinds of entities. So it's a stratified random sampling. So what are the advantages and disadvantages? So this kind of stratified sampling is not representative by no means, so no statistical generalization. It is on purpose not representative because your goal is to hear minority voices. Your goal is to ensure that smaller groups are not overshadowed by the larger ones. This is why you are on purpose creating a sample which is not representative in terms of distribution of variables. It is not random and completely random and so on. You want to hear experiences, you want to understand differences rather than creating a general picture. Another form of multi-stage sampling is a cluster sampling. So in the cluster sampling, the sampling frame is divided into groups and items are drawn from a subset of those groups. So let's say the same story of a Morales survey. So we have a very big company. It has 20 offices around the world. There is no way that a researcher can travel and visit all 20 offices. So instead, the researcher selects 3 offices, stage 1, and then selects 7 participants in each one of those offices. This is a cluster sampling. So we first of all select the subgroups, and then we select cupcakes within subgroups. So this is a different story compared to the, for instance, quota sampling, where we have, the idea was to include elements from every single stratum. This is not the case here. The first stage selection is also a sampling-based selection. It's not a complete selection. So there are different names. Even only if both selections are random, we can say that it is a cluster random sampling. If it is not, then it is an adaptive cluster sampling. We are going to look at it in a moment. So this approach works if the strata are heterogeneous, but very similar to each other. So don't forget, in the quota sampling, we wanted to have strata which are extremely homogeneous, but very different. Here it is exactly the other way around. The strata are heterogeneous. We have both red cupcakes and white cupcakes, but essentially all those strata are the same. So cluster random sampling, as I said before, is a situation when both choices are random. So we first of all select random subgroups and then select random cupcakes. And adaptive sampling is a variant with a difference that, of course, we can sample more if the results are interesting. That's an idea of adaptation. So we do not take the sample as a predefined collection of items, but we adapt the sample as we go. So in a way, this is similar to snowball sampling or respondent-driven sampling we talked about before, because also there we essentially explore as we go. So what does this mean for our advantages and disadvantages? So we need to find a balance. Subgroups should be similar, because otherwise, if we have selected a specific subgroup, we already influence the subsequent choice of items within the subgroup. This is difficult in practice. In the example I was giving with a company with 20 offices, it is very likely that offices are located in different parts of the world, or maybe different parts of the country, and local culture can influence things like morale. So we could not plausibly argue that subgroups are actually similar. What is nice here is that we can find a balance between going broader, so essentially including multiple subgroups, and going deeper, including multiple items. And this is in particular is the case for adaptive sampling. Okay, let us move to the panel sampling. So panel sampling is essentially a very simple idea that the same sample is studied 2 or more times. And it is orthogonal to what kind of sampling strategy has been used. It might have been probabilistic, it might have been non-probabilistic, it might have been mixed. You have determined your sample and you just study it twice. Classical situation when panel sampling is used is the educational context. You typically study students before the course, what do they know about topic X, then they have a course, and then again at the end of the course you study what did they learn about topic X. The same for this morale example. Let's say you are implementing a program for improving morale, so you start by interviewing 20 people. Doesn't matter how you selected them. A year after, you interview the very same 20 people to see whether their attitudes have changed. You could argue, so essentially depending on how your basic sampling strategy was organized, you can talk about non-probability sampling or probability sampling depending on the original panel. Okay, question to you. So we have a study of Andre Meyer. This is one of the studies we discussed last week on Tuesday. It's about this good day and typical day. And we have, as usual, 4 options: A, panel sampling; B, cluster sampling; C, quota sampling; and D, none of the above. And let us start the poll. Okay, so we have 10 answers for D, none of the above, 4 answers for A, panel sampling, 2 answers for B, cluster sampling, and 1 answer for C, quota sampling. So none of the above. This is not a quota or cluster sampling since there are no subcategories. There is no indication of any kind of strata. This is also not a panel sampling because there is it's not that we have selected the same people and we have talked to them twice, or the same project and analyzed them twice. No, it's none of the above. It's a non-standard sampling. This kind of things always also exist. Essentially, you do not need to expect every single paper you might encounter to fit into this typical sampling strategies I've been discussing so far. So those strategies are useful, but sometimes you might need to combine them, or sometimes you might need to do something completely different. Just to give you another example, right? In case of literature review, you might have purposive sampling to this database query followed by a snowball sampling. You can have a combination of the two where you're essentially performing both steps and so on and so forth. So how common are those strategies? Recall that we have non-probabilistic sampling strategies, convenience sampling, purposive sampling, snowball sampling, and respondent-driven sampling, which is an improved version of the snowball. 3 probabilistic sampling strategies, whole frame, simple random, and systematic random, and a couple of multi-stage sampling such as stratified random, quarter sampling, and cluster sampling. So Sebastian Baltes and Paul Ralph, on whose paper this lecture is based, have analyzed 100 articles that have used 179 sampling steps. So this is already an indication that that several articles use multiple sampling steps, either as part of the same research strategy or as part of multiple research strategies, because again, an article might use multiple research strategies. So among those, we have lion's share which are non-probabilistic. So 125, so the largest group, are purposive. 20 are convenience, and there is 1 snowballing. 12 were simple random, 9 used the entire frame, and 1 was stratified random. So 9 studies did not use any sampling at all. So let us look at our research strategies and sampling strategies, right? By no means I want to suggest that this mapping is exhaustive, but it can give you some idea on how those strategies, those sampling strategies are often used in context of the research strategies. And let us start with the field study. So as I said in the beginning of the lecture, sampling in the field study essentially means what field do you want to study, what project or group of projects you want to study. Usually, this field study is something which requires embedment of a researcher in the project and quite profound understanding of what is going on. This would typically be not possible for many projects. You want to select a project either because you have access to those projects, to people who are working in this project, or to companies which are involved in those projects, or because you would like to observe some kind of phenomena, because you, for instance, expect that in large projects, communication is different, or in projects that use multiple programming languages, interdependency between components is organized in a different way than in monolingual projects. So this suggests that convenience sampling and purposive sampling are probably the way to go. as we talked in the beginning, so this field study is also something which we might be thinking about in context of exploration. And this is, of course, also where convenience sampling and purposive sampling make a lot of sense. Another example is the judgment study. So in a judgment study, we want to find expert opinions. And this is a call for purposive sampling. It can be done in a more intricate way, for instance, using quota sampling, right? So we have multiple strata and then purposive sampling within each stratum. But essentially, it's a purposive sampling. You are asking people not because they are random, but because they have specific expertise that you are looking for. If you are looking for lab experiments, we typically work with either stratified random sampling or with quota sampling. This is because we typically would like to ensure that laboratory experiments involve participants or involve systems of different kinds, and we do not want any single kind to overshadow another one. Sample studies typically use some kind of combination samplings because you start with typical purposive elements like I'm looking for GitHub because it's the most popular platform. I'm looking for, I don't know, Java because it's one of the most popular languages. And then you might have a random sample. For instance, if you can find a list of all Java projects on GitHub and select things randomly, or you can do further purposive steps, like claiming that I'm only interested in projects which have at least 10 forks and 15 watchers. So this could be yet another way of defining a sample for a sample study. Snowball sampling, purposive sampling, again, or of course, respondent-driven sampling, they're all possible. They're more likely if we are looking at human beings, if the sample study is considering human beings, right? After all, this respondent-driven sampling has been designed for studies involving human beings. So let me summarize what we have been talking about today. So we have started by introducing the notion of sampling. Sampling is the process of selecting a smaller group of items to study from a larger group of items of interest. The smaller group is known as a sample. This larger group of items of interest is known as the population. This population is usually represented by means of the sampling frame, which is essentially a list of all items in the population. Sampling frames are often unreliable, inadequate, or incomplete. Given your research question and your research strategy, there may be different ways of perform sampling. Most common ones are non-probabilistic ones, convenience sampling and purposive sampling. So essentially, looking at projects or talking to people simply because they are available, because we could analyze the data, or because we could interview people. So convenience arguments, or because they have one or more interesting features. For instance, because they they involve at least 50 software developers, if we're talking about projects, because they have specific expertise, and so on and so forth. Snowball sampling and respondent-driven sampling are based on the idea of referral. When one person recommends, for instance, in the context of interview, another people to interview, one paper cites other papers, or one library depends on other libraries. So respondent-driven sampling is an improvement on the snowball sampling, which tries to compensate for problems of oversampling well-connected items and opinions being overshadowed by well-connected elements, clusters. The next group of sampling strategies are probabilistic. So we talked about the element of randomness and the importance of actual random sampling, actual randomization in probabilistic sampling. And two most common ones are simple random and systematic random. Whole frame is also quite commonly used, at least as long as it is feasible. We have also seen that those probabilistic and non-probabilistic elements can be combined in different ways. We have seen several examples such as stratified sampling or quarter sampling. We have also seen cluster sampling, essentially depending on what kind of elements we combine and how those series of decisions influence each other. Finally, panel sampling is simply a repeated sampling of the same items, the same people, the same projects. And at the very least, we have seen a couple of mappings of those sampling strategies and research strategies we have discussed last week. So on Thursday, we are going to move to the first actual data collection mechanism, and those are interviews. So we are going to talk about how to talk to people, and we will see that it's not only about the questions you ask, but also about how do you ask those questions. I will look at the answers you've been given for the first quiz, and we will release the answers before the end of the day. Thank you very much. Goodbye.